Welcome back to this module on dynamic exploitation of ILP. The topic of this final lesson of this module is limitations of ILP. The motivation for this lesson is as follows. Should we keep on investing in exploiting more and more ILP? That means, should we continue developing processes with higher issue width, deeper pipelines, better branch predictors, more reorder buffers and reservation stations, and so on? Or should we find other ways to increase the performance? For example, by exploiting data level parallelism using vector instructions, or by exploiting thread level parallelism using several cores. To find an answer to this question, in this lesson I will present results that show how much instruction level parallelism is available in typical programs. So the question addressed in this lesson is, how much ILP is available in the programs that we want to execute on our processor? In other words, how many instructions can be executed in parallel in the targeted programs? This brings up another question, namely, how can we measure this independent of an actual implementation? If the processor can issue at most 4 instructions per cycle, then obviously the highest IPC that can be achieved is 4. But obviously this doesn't tell us what the maximum IPC is for a particular program. We can solve this problem by assuming an ideal or perfect processor. In such a hypothetical processor, all implementation constraints are removed. Instead, ILP is limited only by the data flow of the program. That means that if an instruction is data dependent on a previous instruction, then these instructions need to be executed sequentially. Otherwise, they can be executed in parallel in this ideal processor. So how does this ideal processor look like? First, this ideal processor has unlimited functional units. So there will be no structural hazard because an instruction has to wait because another instruction is using the functional unit it needs. Second, our ideal processor has an infinite number of renaming registers. That means that all name dependencies, write after write and write after read hazards, are eliminated. Third, our ideal processor performs perfect branch and jump prediction. That means basically that at the start of the program, all instructions are available for execution. This is equivalent to having a processor with perfect speculation and an unbounded buffer of instructions available for execution. Our ideal processor also performs perfect memory address alias analysis. All memory addresses accessed by the program are known at the start, and a load can be executed before a store provided they access different addresses. Fifth, perfect caches are assumed. That means that all memory accesses take 1 clock cycle. Finally, in the study presented in this lesson, all instructions are assumed to have a latency of 1 clock cycle. That means that a sequence of dependent instructions can issue in consecutive cycles. Together, these assumptions imply that only true data dependencies limit the amount of ILP that can be achieved. The study presented in this lesson used the Spec 92 benchmarks. I will focus on 6 of them. 3 integer benchmarks, GCC, Espresso and Lee, that were written in the programming language C, and 3 floating point benchmarks, FPPPP, Doduk and Tomcat V, written in Fortran. This table also contains a short description of each benchmarks. The programs were compiled using the standard MIPS compilers with maximum optimization. Thereafter, the programs were instrumented and executed to produce a trace of instructions and data references. Using this trace, every instruction can be scheduled as early as possible, which can be used to obtain the IPC achieved on the ideal processor. This figure shows the IPC achieved by the perfect processor on the 6 considered benchmarks. The results for the integer benchmarks are colored orange and the floating point benchmarks are colored violet blue. Several observations can be drawn from this figure. First, the amount of ILP is significant, ranging from 18 for Lee to 150 for Tomcat V. Second, the integer benchmarks exhibit less ILP than the floating point benchmarks. This is not surprising since scientific programs usually process large matrices and arrays, and often the computation on each element is independent of the computation on other elements. Third, for the benchmark Li, an IPC of only 18 is achieved. This is because Li has many short dependencies, meaning that there are not a lot of independent instructions between each pair of dependent instructions. Next, I will present results for a processor that might be realized in the near future. I call this processor a realizable processor 2020 ? Or RP 2020 ? And compare its attributes to those of the Power 7 and Core i7 processors. RP 2020 has an issue width of 64 instructions per cycle with no issue restrictions, meaning that all issued instructions can be of the same type. For comparison, both the Power 7 and the Core i7 have an issue width of 6. So RP 2020 has an issue width more than 10 times the issue width of the widest issue processors of today. RP 2020 uses a tournament predictor with 1K entries and a 16-entry return address stack. The branch predictors used by the Power 7 and the Core i7 are slightly more advanced, but the branch predictor is not the primary bottleneck. RP 2020 can also perfectly disambiguate memory addresses. As before, this means that all memory addresses referenced by loads and stores are known, and a load can be executed before a store provided they access different addresses. This is slightly more ambitious than current processors, which perform memory disambiguation dynamically at runtime. Finally, RP 2020 has 64 additional integer registers and 64 additional floating point registers to perform register renaming. This is slightly less than the most aggressive processors of today. The Power 7 has almost 200 renaming registers, while the Core i7 has 128 entries in its reorder buffer, although they are not split between integer and floating point entries. I also need to remark that it is assumed that all instructions have an execution latency of 1 cycle. This also reduces the number of reorder buffer entries required, since an entry will be occupied by a certain instruction for a shorter time. This figure shows the IPC achieved by the RP 2020 processor for different window sizes. The window is a set of instructions considered for parallel execution. In the designs we have considered so far, the instruction window consists of all instructions which are in the reorder buffer. Many observations can be made from these results, but I will focus on two. First, the IPC achieved for the integer benchmarks GCC and Espresso has dropped tremendously compared to the ideal processor. Even if the instruction window has an infinite size, indicated by the light blue bars, the IPC decreased from 55 to 10 for GCC and from 63 to 15 for Espresso. For Li, the performance decrease is smaller, from 18 to 12. This is because Li doesn't achieve a very high IPC on the perfect processor due to its short dependencies. The second main observation that can be drawn from these results is that the floating point benchmarks still achieve a higher IPC than the integer benchmarks, but the IPC reduces rapidly when the instruction window size is decreased. For example, for the rightmost benchmark Tomcat V, the IPC is 22 when the instruction window size is equal to the issue width, namely 64, whereas the IPC is 56 for an infinite window. Obviously, the maximum IPC is 64, since that is the issue width. These results point to a key difference between the types of programs. The availability of extensive loop-level parallelism in the floating points benchmarks FPP, PP, and Tomcat V means that the amount of ILP that can be exploited is mainly limited by the instruction window size. For the integer programs, other factors such as branch prediction accuracy and register renaming are all important limitations. This limit study also had a number of limitations, however. First, the study eliminated all register write after write and write after read hazards, but it did not eliminate these hazards in memory. As shown before, a write after read hazard in memory occurs if a load reads from an address that is written by a later store, and a write after write hazard in memory occurs if two successive stores write to the same address. Although it might seem that such hazards are very rare, especially write after write hazards, They do arise due to the allocation of stack frames, and they are unnecessarily limiting. Second, the benchmarks simulated in this limit study contained unnecessary dependencies. In particular, the compiler did not perform loop unrolling. Because of this, the instruction that increments the loop index depends on the instance of itself from the previous iteration, as illustrated here. As a result, a loop that iterates n times always requires n cycles to execute. The study did consider the effects of loop unrolling by manually unrolling frequently executed loops, but only in a limited way. A natural question to ask is, how can we exceed the limits of this study? One idea that has been proposed is to speculate along multiple branch paths. In other words, to speculatively execute both paths after a branch. This only makes sense for a limited number of branches, since the required hardware resources grow exponentially. Given this high cost, commercial designs have devoted more hardware to predict and speculate on the correct path. Another idea that has been proposed is called value prediction. The idea is to predict the value that will be produced by an instruction and to execute the instructions that depend on this instruction speculatively using the predicted value. This makes sense only for instructions whose results are predictable, such as loads from a constant pool and increments of the loop induction variables. More than 100 scientific papers about value prediction has been published. It was a very hot topic in the late 90s, but no commercial processor has implemented it yet. I conclude this lesson with some challenges of exploiting instruction level parallelism. These challenges motivate the lessons to come. In this module, we have seen that dynamic exploitation of ILP significantly complicates the hardware. So the first challenge is to reduce the complexity of this hardware. One idea could be to move part or all of the complexity into the compiler. This is actually the idea behind very long instruction word processors, which I will discuss in the next module. The second challenge is how to exploit more ILP if the hardware or the software cannot find it. One idea is to give back this task or part of it to the programmer. In the third module of this course, I will discuss single instruction multiple data SIMD instructions, which are kind of based on this idea. Another challenge is how to efficiently use the available ILP resources. A processor might be able to issue and execute 6 instructions per cycle, but the IPC achieved for a single thread is rarely more than 2. One idea is to execute multiple threads at the same time and share the ILP resources. This is the idea behind core multithreading, which I will discuss in the fourth module of this course. The fourth challenge is how can we provide even more compute power, more ILP resources, when a single core is not sufficient. This leads to multi-core designs, which I will discuss in the fourth course of this specialization. Finally, some sample questions. Here are 3 statements. You should indicate if the statement is true or false and also why. This completes this lesson. Thanks for watching. As announced before, in the next lesson I will discuss VLIW processes. Hope to see you back.